So I'm going to be talking about geometry with predictions, and what I'm going to explain is mostly based on joint work with Timothy Chan and Panos Giannopoulos. And actually, so when I mentioned or when we were discussing by what to talk about, and if you look at the title of what I promise I will talk about, it's about Delaunay triangulations with predictions. But then I changed things into geometry with predictions because I want to be talking of two works. One of them is going to be the promise, the Delaunay triangulation with predictions, and the other one is going to be about searching Euclidean spaces with predictions. So I didn't lie too much with the title, but let's say at only 50% in a way. I decided for this change because somehow in the talks I give, I prefer to talk, to have more emphasis on breadth instead of depth. So people in particular can reconnect if at some point they get lost. So I will start talking about what does it mean actually algorithms with predictions. So what is this concept? And then the two research pieces that I mentioned. So as I already mentioned, one of them is with Timothy and Panos. The other one is only with Panos. Okay. So what are algorithms with predictions? So we are used to have algorithms where you have certain input, some data, and you want to compute something. Then a prediction is additional information that you're given on the side of the data, so besides the data, which could be inaccurate, it could be noisy, it could be good information, or it could be even misleading information. But the idea is that when the information is not misleading, when it's useful, it should assist the algorithm is more effective. By effective, it could mean that the algorithm will be faster. It could be that the algorithm will be an approximation factor will be better. It could be also a model of randomicity. I mean, that it tells you that the data is chosen with respect to certain distribution, where the distribution you are given could be misleading also, or it could be close to the truth. And then the point is to use the input data as usual and the prediction to give an algorithm and parameterize how good the algorithm is depending on how good the prediction is. So what you would like is when the prediction is good to get a better algorithm that works. I mean, the algorithm is always the same, but when the prediction is good, the algorithm performs better. And when the prediction is bad, okay, you would like to don't lose too much. Okay, so you shouldn't just blindly trust. And here there are a couple of toy examples, I would say. So one of them, which is a classical one, is searching for an element in a sorted array. So you have a sorted array, and you're given an extra element, and then you would like to know whether that element is in the sorted array or not. So that usually you would use binary search for that. But here, as a prediction, you could be given a finger to an element in the array. You could tell, I think that the element that I'm searching for is around this part of the array. So a pointer to the part of the array. And then that can help for the binary search. So the distance in the array from the finger to the actual location of the element, or the one that is the smallest one that is estimated larger, or something like this, that would be a parameter that helps you to provide a better or analyze the algorithm more carefully. So in particular, in such a setting, what you could do is an exponential search followed by a binary search only for a certain part of the array. If you do this, the time you spend is logarithmic in the distance in the array instead of logarithmic in the size of the array. Another toy example would be sorting a list of numbers that is given almost sorted already. Okay, so in this case, the prediction is the list itself. So they give you a list, they ask you to sort the elements in the list, and the list is given almost sorted. And now you need some measure of how sorted the input is. So you could be looking like the number of inversions that you need to sort it, or you could look at how many increasing runs you have inside the input list, or different measures. But this is the idea of algorithms with predictions. I mean, you have input data as usual, and then additionally you have certain additional information. So this concept of algorithm with predictions, so the way how I learned about it is by a chapter in the book Beyond the Worst Case Analysis of Algorithms. There is a survey by Mitzenmacher and Wasilewski. And I think it's a really nice introduction. Actually, the binary search example is provided there at the beginning. And I would say that there is a growing amount of work that is using this concept or this approach or this paradigm. And there has been some workshops in DAXTool, in Stock, in iCal that are focusing on this kind of things. There is also a very nice web page, Algorithm with Predictions. There is listing papers that is working on this kind of topic. And well, I just checked yesterday, there are almost 400 papers by now. So, of course, when you hear about a new paradigm, like algorithm with predictions, you have a history of working on computational geometry, and then you wonder, okay, what can we look at this paradigm? Can we use this paradigm in computational geometry? So you're interested in knowing what kind of objects can we have here. And this is basically what I'm going to be talking about today. A couple of problems that lie here inside. Computational geometry, intersection algorithms with predictions. Let me mention a couple of previous works that they existed before the concept of algorithm with predictions existed, but that they can be reinterpreted now as algorithms with predictions. I mean, so, quite often you do things and with time you get perspective and you can interpret those things differently when you have a different perspective. And that's this case. So there is a paper by Iacono and Langerman which they look at the point location problem in the plane. So you have a subdivision of the plane into cells, and they were looking at the point location problem. So the standard thing is pre-process this subdivision of the plane, that when somebody comes with one point, you can tell in which phase of the subdivision the point lies on. And they look at the concept when you're given a point, I mean, you're given a query like this, and you're given a phase where you think like, okay, the phase containing the query point is hopefully near this phase. So you're given this phase as a prediction. And then can this help to make point location? So this kind of a scenario shows up, for example, if you have an entity that is moving in the subdivision and you make point location in the subdivision, but not too often. And then you have this kind of thing, like, I mean, before the point was somewhere here, the entity was somewhere here. So you expect that the next phase that will contain the point, the entity will be nearby. So can you make point location where instead of using, well, you have to define some concept of distance between the phases, the phase that is the correct answer and the phase that is the prediction, and they define a distance, and well, you have to work out quite a few things, but that follows this paradigm of having a prediction. I mean, a point you want to locate and a phase that hopefully is going to be near the answer. The principle could be very far off also. Also, under the umbrella of this paradigm falls this of computing geometric objects with additional information. So below I will provide more information about the Delaunay triangulation, but that's this kind of thing. I mean, in computational geometry, there is quite substantial amount of work that follows this paradigm. And one could also interpret this geometry with predictions as an extension of verification of structures. So if we go back here to this kind of examples, I was mentioning is like, for example, if the input is given sorted, there is nothing to do. So in particular, you should be able to check if the input is sorted quickly, faster than sorting. And this is the kind of paradigm that follows here on verification. If, later we will talk about the Delaunay triangulation in a couple of slides. And then the question in such a case is like, well, if I give you something that I claim is a Delaunay triangulation, can you actually check if it's a Delaunay triangulation? Okay. So that was about algorithms with predictions. So as a new paradigm or concept that is worth to use as a new perspective. And I'm going to be talking about the first work, which is about Delaunay triangulations with predictions. So the Delaunay triangulations, I'm actually not 100% where everybody knows or not. This is a geometry seminar, so I would expect so. But I would suggest it to perhaps still mention what it is. So this is the Delaunay triangulation for this example, for this point set. We are going to be in the plane only. And one way to define the Delaunay triangulation is the following. You iterate over all triples of points. Whenever you look at 3 points, you look at the circumcircle through those 3 points. And if this circumcircle does not contain any other input point in the interior, then you put a triangle. And you do this over all triples. And this is assuming general position. This is a definition of the Delaunay triangulation. The standard warning that we give to students is it's not obvious that this gives a triangulation, because we are telling when you have to put a triangle inside, and in principle or a priori, two such triangles could be intersecting. But one of the standard results in computational geometry or in discrete geometry is that this is indeed a triangulation, assuming general position, meaning no 4 points are collinear, co-circular. Okay, so the Delaunay triangulation is the dual object to the Voronoi diagram. So this is the same point set in both cases. And the Voronoi diagram would do is a subdivision of the plane into cells. So this will be a cell for this point, which is the set of points that have this, well, the set of points in the plane that have one of the input points, this one as the closest input point. And the dual object of this is the Delaunay triangulation. So you are connecting two objects because this cell and this cell, they are sharing here a Voronoi edge. Again, this definition is not obvious that actually gives a triangulation, because there are things like this that they are visiting over a couple of cells, Voronoi cells. But again, it's like standard material to argue that these are a triangulation. Okay, so the Delaunay triangulations is one of the standard objects that we use a lot in computational geometry. So they can be defined by these triangles with the empty circumcircle I just mentioned, or the dual to the Voronoi diagram. They also maximize the vector of non-decreasing angles over all triangulations of the point set. It's always a partition of the convex hull, and it appears everywhere. We know how to compute in n log n for n points the Delaunay triangulation. And we have a lower bound, of course, in certain model of computation that you cannot do better than n log n. And Delaunay triangulations is one of the classical problems where we have several techniques of how to approach to them. And one of the standard ways to look at it also is that it's a two-dimensional extension of sorting. So sorting points on the line is actually computing empty intervals, maximal empty intervals, which can be seen as one-dimensional disks that have to be empty and should be spanned by a couple of them. So whenever you think of something sorting in the line as a problem, one of the standard extensions is Delaunay triangulation. The Delaunay triangulation has this locality property that allows you to check if a given triangulation is indeed the Delaunay triangulation. So basically, for every triangle, you have to check its three neighbor triangles. Okay, so if you look at this triangle, you look at the circumcircle, and then you should check if there is any point inside that circumcircle. But in fact, it suffices to look at the points that are in the adjacent triangles. Okay, that's a standard property. And this means that for every triangle, you have to check a constant number of neighbors, so a constant number of points, whether they are contained in the circumcircle. So a consequence of this is that you can test in linear time if a given triangulation is the Delaunay triangulation. Okay, and then you have this discrepancy. So I can build the Delaunay triangulation in n log n. We know that you cannot do better than n log n. And then we can test if a given triangulation is the Delaunay triangulation in linear time. And now the question is there something in the middle? And before answering that, let me mention another problem. which is perhaps for people not working in geometry, perhaps it's more natural, which is that of the Euclidean minimum spanning tree. And that's an optimization task. So even if you don't see why the Delaunay triangulation should be an useful object, I think that everybody will understand that the Euclidean minimum spanning tree is a very natural object to look at. And it's you want to connect the set of points using a spanning tree, and you want that the spanning tree has minimum length, looking at the Euclidean length. And you are not allowed to use staggered points. So you're not allowed to use additional points. You should always be connecting two input points. And it is well known that the Euclidean minimum spanning tree is a subgraph of the Delaunay triangulation. And that gives a way to compute the Euclidean minimum spanning tree by first you compute the Delaunay triangulation, and then you select a minimum spanning tree of the Delaunay triangulation. And that's an algorithm that takes n log n, because the first step is computing the Delaunay triangulation that takes n log n. Once you have the Delaunay triangulation, you can compute the Euclidean minimum spanning tree in linear time, because the Delaunay triangulation is a planar graph. Computing the minimum spanning tree of a planar graph can be done in linear time. So the bottleneck is computing the Delaunay triangulation. Some people might know, some not. This is less standard already. That if you give me a candidate, if you give me a spanning tree and a claim that this spanning tree is the Euclidean minimum spanning tree, how fast can you check if the claim is true? So you can do this in n log star n. So log star is the iterative log, how many logs you have to take to get below a constant. And this can be done in expected time, n log star n. This is a result of de Villers, 92. And you could do it in linear time also, deterministic, by a result of Chin and Wang from 98. So in both cases, what they do is, if you give me the true Euclidean minimum spanning tree, I can use that to speed up the computation of the Delaunay triangulation. So they provide linear time deterministic, and the previous paper was n log star n, expected time. So the basic idea is, if you give me a candidate to be the Euclidean minimum spanning tree, I run these algorithms that if you give me the real Euclidean minimum spanning tree, I will get the Delaunay triangulation. Now, if you give me something that is different, it might be that the algorithm crashes somewhere, or otherwise it will return me something. This something you have to check its Delaunay triangulation, and then you have to compute the minimum spanning tree from that. Okay, so that would be the overall idea. So in general, what this means is that we can compute the Euclidean minimum spanning tree, we can check it, a candidate, faster than n log n. So there is this idea. Okay, so closest related work to the results I'm going to explain now. It's computing the Delaunay triangulation with additional information, like some Euclidean minimum spanning tree or some other objects I will explain. And this relates actually to, okay, this is what I was mentioning before. And then related to this would be the merging two Delaunay triangulations. So it is known that if you give me the Delaunay triangulation of point set P and the Delaunay triangulation of a point set Q, then you can compute the Delaunay triangulation of P union Q. And that can be done in linear time, or splitting. So given the Delaunay triangulation of a superset, given the Delaunay triangulation of a superset, compute the Delaunay triangulation of a fixed subset. And in a way also the verification of the structures I was mentioning. So given a spanning tree, is it really the Euclidean minimum spanning tree? So this will be the closest related work to this paradigm that I've been trying to explain. Okay, so sample of the kind of results that we have here and that we call Delaunay triangulation with predictions. So consider the following scenario. So you're given a set of n points in the plane, and you're given a triangulation of the point set. hopefully, I mean, you would like that this triangulation is the prediction. So hopefully this should be close to the Delaunay triangulation, but doesn't need to be the Delaunay triangulation. Okay. So what is the measure of the prediction? How good is the prediction? So you look at the number of edges that is in the triangulation that do not belong to the Delaunay triangulation. Or vice versa, because all triangulations of the same point set have the same cardinality, the same number of edges. You could be looking at how many edges of the Delaunay triangulation do not show up in the triangulation I'm given. Okay. So if you're given the Delaunay triangulation, this number is 0. But in principle, you could be having a portion of the edges that is wrong. So this would be such an example. So here is a triangulation. I draw here some red edges that are the wrong ones. They do not belong to the Delaunay triangulation. And from this, we would like to compute the Delaunay triangulation. So this is the problem that I would call Delaunay triangulation with predictions. And what kind of results we have here. So you can compute the Delaunay triangulation in n plus d log n expected time. And I think that one should interpret this as a smooth interpolation between the linear time for testing when you are given a Delaunay triangulation, or the n log n where you are given just a garbage triangulation, a triangulation that is far off from the Delaunay triangulation. Okay, but you could think like perhaps a ratio of 1 over log n of the edges are wrong. So it could be like n over log n of the edges are wrong, and in such a case, you can still get the Delaunay triangulation in linear time. This is optimal. That's the good news. It's randomized. That's the not so nice news. And we also work on a deterministic algorithm. And then the current deterministic bound we have is this kind of running time. N plus the number of wrong edges times log cube of n. Another kind of result that we have, so another sample is with respect to the Euclidean minimum spanning tree. And that's the reason I was explaining this. So we are given as input a set of endpoints in the plane, and we are given a spanning tree of the point set, hopefully quite similar to the Euclidean minimum spanning tree. The measure of the prediction, how good is the prediction, is the number of edges that are wrong. So the number of edges that are in the tree but are not in the Euclidean minimum spanning tree. So in this setting, the running time that we get from algorithms is n times the number of wrong edges log n plus the number of wrong edges times log n, and then we have this log star n multiplying everything. So when d equals 0, we recover the n log star n for testing that follows from the algorithm of Olivier. And it's not that we are recovering it differently, because actually we are using many of the ideas from that paper. Okay, so it's not really a new algorithm, but it's an extension of the algorithm of De Villiers for this. So for me personally, I mean, I work in geometry. Most people here, I guess, at this seminar because they like geometry. But this is a problem that to me is much more surprising and much more interesting to explain to an outsider. Okay, because this is a problem that without working in geometry, it's easier to understand, I think. Another example of our results is a probabilistic model. And one of the reasons why I want to explain this other result is because it introduces a new paradigm or a new model of predictions. So in this case, the mistake or the noise is probabilistic. So the way how we formulate this is like from the Delaunay triangulation, you select a subset of the edges with certain probability and independently. So you go over the edges, and for each one of them, you perform an independent experiment. Do I keep it or not? So this gives you, I mean, some edges remain. So the probability that an edge remains is rho. and then you extend the edges that remain, you extend them to a full triangulation. You could also think of another scenario, but that's fine. And then the measure of the prediction is this probability, rho. And in this case, we can compute the Delaunay triangulation with high probability times, n log n plus n of log 1 over rho. Okay. And for example, if rho is 1 over log n, this means that a really small fraction of the edges of the triangulation is kept. Then this is augmented into triangulation, and in such a case, we can still recover the Delaunay triangulation faster than n log n. So the way how one reaches this is because, of course, so I was telling before the number of wrong edges as a measure. There are other measures you could be using, like the number of violations. Like when you look at one circumcircle of the triangulation, how many points are inside? You could be looking at the maximum over the triangles of these violations. And there are several different measures. I mean, in the paper, we study quite a few of them. The number of wrong edges is the most natural, perhaps. And this one with probability is also like, I think, very natural. I don't know how much to explain about the idea. So this so far has been publicity. It's like 30 here in Ljubljana. So let me explain you an idea that show up during the research in very non-precisely. I'm going to explain the idea, but one of the issues that follow up and to get a weaker bound actually. So consider the problem of we are given a triangulation, G of a set of points P, and we want to compute the Delaunay triangulation. So one of the original ideas that we were having was the following. So you look at a triangle, when you iterate over the triangles, when you look at a triangle, you look at a circumcircle, and then if inside that circumcircle there is a point, just remove the three edges of the triangle. I mean, you don't know which, I mean, you know that one of them is wrong, you know which one cannot be, but it's just easier to remove all three because that's a factor three. I mean, you're going to be removing 3 times more edges. And now when you start repeating this process, you run into this kind of issue that you have a certain phase. And let's say that you're looking at this triangle, and then you look at the circumcircle, and then you have a point inside this point, but that's not a point that is in the same phase. That is, I mean, so usually for this triangle, you would like to be looking at the contiguous phase. So you are not going to detect that this point is there, or that's not a local test anymore. On the other hand, it could be that when you look at this triangle here, you are looking at the circumcircle, and then here you have some points inside. So you would be deleting this face, these 3 edges. Okay. So what you want to do is when you delete this guy, I mean, when you delete these 3, you get this kind of a scenario. And now for this triangle, this vertex, this point that was outside, I mean, that was not cofacial before, now it is cofacial. So one way to handle this is you have like a set of disks that are spanned by this kind of triangles, and you have a set of points, which are those that are cofacial, and you want to find incidences between them. You want to figure out is a point inside a disk. And you want to do this locally, I mean, so only for things that are in the same phase. And that can be phrased as a dynamic data structure where you have dynamic disks, you have dynamic points, and you want to know where there is an incidence between a point and a disk, because that's what allows you to do this fast. And then there are data structures for this. So Timothy Chan has one classical data structure that then has been improved, because this, when you lift it to 3D, the problem to the paraboloid is basically incidences between half spaces and points, where both have to be maintained dynamically. Okay, so with current data structures, you get this kind of, well, a log4 and to detect all such violations. And that was one of the ideas that we employed here at the beginning, which actually didn't make it. Well, I think now it's in the appendix in the archive version, but because we improved here to a 3 in a different way. But I like this idea, one, because it is simple, and because there is hope that it will still be improved if the data structures we are using will ever get improved. There are, of course, some things to argue. Like, I mean, once you have for all phases, this kind of locality test is passed, then all the edges that are left are actually part of the Delaunay triangulation. That's something to argue. There are a few classical geometric tools to be used. This was another idea I had to explain, but I will skip this, which was about how we approach how we adapt the approach of the Villiers. So let me skip this and move to the next problem because of time. If I speak too fast later, I can come back to this one. Okay, so we have finished the first part, the Delaunay triangulations with predictions, and I'm going to be talking about a completely different problem that requires much less background, actually. Searching in Euclidean spaces with predictions. Let me explain you a classical search problem. Many of you has probably heard about it. So we are in the line, so one dimension. We are at the origin, starting the search for a target. So we know that the target is at distance 1 from the origin, but we do not know where the target is. And then we want strategy, how to search for the target. So basically it would be, walk to the left certain amount. If you didn't find it, then go back to the left and so on. And then what we want to do is to minimize the competitive ratio. So the competitive ratio, what is it? Is you want to look at the length of the search path, how much are you walking, divided by the length of the shortest path. If you would know where the target is, you would go directly there. Okay, so one of the standard ways to do this is exponential search. So you walk in one direction for 1. If you don't find it, the target, then you go back to the origin and walk to the other side for 2. If you don't find it, you go back to the origin and the other way 8, and then 16, and then 32, and so on. And this gives a competitive ratio of 9. And this is a problem that has been studied and rediscovered and rediscovered and studied and rediscovered. So here there are a few references. You can conclude from the years that is classical things by now. So 9 is the optimal competitive ratio. I mean, it is known that you cannot do better than 9. There are at least 4 different proofs of this I'm aware of. And then people, of course, once you have a traditional problem, it's completely solved. So you look at variations of this. So one of the variations, which is very much related to the predictions model I was mentioning before, is if you have the additional information that the target is at certain distance. So you know the target is at distance 1 at least, and it's at distance d, let's say at distance 1000. So let's say that somebody tells you the distance to the target is between 1 and 1000. Can you get a better competitive ratio with this information? So this was a study by Hipke and et al. And Bose et al. Another standard generalization has been to multiple rays. So instead of having, I mean, the case of the line is 2 rays, but you could be having 20 rays. And then it's not obvious how to do it, but you could be working like, let's say 2 in one ray. If you don't find it, then you move 4 in another ray, otherwise 8. And that would be some technique, with some approach, and you would like to study that. So if you look at search problems in, let's say, 2 dimensions or in higher dimensions, you will never hit the target. Okay, So, I mean, there is no way to find the target in the plane because, I mean, in the one-dimensional line, you know that you will sweep over the target at some point, but in the plane, that's not the case. So in the plane, one of the variations that were studied that I think is very nice is you start at the origin working, you're looking for unknown target, and then what you do is you keep a leash or a cord between your current position and the origin. And then you claim that you detect the target when this cord sweeps over the target. Okay. So Gall introduced this problem and he gave an spiral search where the competitive ratio is 17.289. So this comes because you want that, I mean, the spiral should have rotational symmetry. I mean, any strategy that is good should have such a symmetry with respect to rotations. And Langetep showed that actually this spiral search is optimal. As I was mentioning, without additional information, you cannot do anything in 2 or 3 or 4 dimensions. One of the reasons, because the first time I thought about this, I was wondering, is this true? You know, there are these kind of curves that they cover the disk. So what you need to argue is that there exists no curve of finite length that covers the disk. So,
Hello, I'm listening to a Zoom thing. The dog's in her cage.
sorry?
What did you say? You're talking to.
If I repeat what I said? I didn't understand the question. Okay, so let me continue. There is, okay. So what this means is that you need some additional information if you want to find the target. And then we realize that this is a very nice scenario to use predictions. So what could be predictions? So you want to have additional information. Okay. So in the context of graphs, there has been actually such a research quite recently, but our model is different, but this is a nice also point of view. In a graph for a target, so they look at the model where at every node you have the distance to the target stored, but some nodes have wrong information. Okay, and then you would like to be able to find the target by working in the graph, and the number of steps you make should be something proportional to the number of nodes that have wrong information. Okay, so this is what was studied here. This that I mentioned before, this research, this could be interpreted as predictions. And so you have a linear search when you have additional information of the distance to the target. Okay, so what we did is to introduce actually a new model, which in my humble opinion is very natural, which is we are in dimension D, we could be thinking of the plane, D equals 2. We start the search at the origin, and then there is an unknown function that we call a C prediction that tells you the distance to the target up to an approximation factor of C. So for example, if C is equal to, what this means is wherever I am, I'm going to be getting a number, and this number is between the correct distance and 2 times the correct distance. Okay, and of course the question is, with such a information, can I find the target? Can I reach the target? Okay, so we look into, I mean, so this would be the one-dimensional case. So when you're searching here, you have here the correct distance as a function. Here you have 3 halves, and then you have some function here that is giving you the prediction. And we want to find a path or a search strategy that will describe a path that when you follow the path, you will reach the target. And you would like to don't walk too much. So of course you want the competitive ratio to be small. So again, it's like the length of the search path divided by the shortest path. You would like, this is a competitive ratio, you would like this to be as small as possible. Okay, so when we look at this problem, so we got, I know that a posteriori, you might think that the problem is natural or is not natural, but definitely I think that the contribution is that we introduced the problem. Then we gave a search strategy that has a certain competitive ratio. And here we realize also that there are two different scenarios. So do you know the approximation ratio or you do not know the approximation ratio? I mean, so do you know that it's a 2 prediction, a factor 2 error, or you know that there is a certain constant you do not know that gives you the estimate to the distance? A feature of our search strategy is that we have bounded length, but we are making an infinite number of terms. And this is unavoidable. Okay, if at some point, I mean, because of continuity, you need to keep looking to get information, and this information forces you to change. Okay, so this is some of the things that we had to argue. Therefore, we reach the target actually by continuity. So we are getting epsilon close for every epsilon, and therefore you reach the target. We also gave a lower bound with a certain uh, competitive ratio that works for any deterministic or randomized strategy. So of course the constant here and the constant here is very different. It's exponential in the dimension, so that's not very surprising. But here we have like 5 times c, and here we have like c over 4. So they are very different. And I will explain you now the main ideas. They are really simple. So I expect there is a lot of space for improvement. So how do you get the upper bound? So basically, we built a sequence of points where the estimate to the target decreases geometrically. Okay, so we start at the origin, and then we compute a point, and then another point, and so on. And the prediction, the lambda values we are getting at this sequence is geometrically decreasing. So how you do it? So it's quite simple. So at some point, at some time, you are at some point, you have this estimate, so you know, because the estimate is always an overestimate, you know that the target is contained in this ball. So then you cover the ball using an epsilon net, or an epsilon that is, okay, the current value, the current estimate divided by 2 times the approximation factor c. So you cover this with these balls, and then you just go through the centers of the ball. And then what happens is either in one of them, you will be decreasing the estimate, and then you zoom there and continue there, or you will never be decreasing the estimate, but that means that the current C you are using is wrong. So then you double the C. Okay, so this would be for the case of unknown C. If you know the estimate, I mean the approximation factor C, then you know always that one of these points in the net will be good. So by traversing them, you are fine. And this gives you the competitive ratio I was mentioning before. Okay, so just go to them until one that the estimate will decrease by at least half, and then you zoom there. And you are adding some things that have a certain ratio, and then you are decreasing this by 1/2, and then by 1/4, and then by 1/8. So the length of this curve converges. And because you're getting arbitrarily close to the target, eventually by continuity you're reaching it. I mean, it's nothing very deep. In particular, here we are neglecting a lot of information. Okay, so in general, if you look at this kind of thing, whenever you make a query in this point, you are getting an annulus that tells you that the target has to be inside this annulus. Whenever you make the query in this point, you are getting another annulus. So we are not using actually this annuli at all. Okay, we are just making something very rough. For the lower bound, the way how we approach to it is for each target. I mean, so you look at the ball, and then you construct a family of functions, all of them being C estimates, I mean C predictions. Whenever you look at two targets, so let's say a target here and a target here, I mean, so here inside and here inside. So the C prediction functions are the same everywhere outside this part and this part. And then in these disks, they are different, the prediction functions. So basically, the prediction function consists of a plateau. I mean, here it's constant for all functions. Then here you are getting a cone because it should be at the target, it should have value 0. And outside, it's just growing nicely. So this is the way how it looks in 1D. I mean, this is the analog. I can make this drawing. I cannot make the real one I would like in 2 dimensions. So here is in 1D, you are looking at one target and one function looks like this. Okay. The other function for this target looks like this. So unless I visit this part and or this part, I cannot know which one of the two functions is the correct one. So in principle, both targets could be alive. And if I'm moving between here only, all the way, it could be that the target is on one side or is on the other side. So I need, for this target, I need to visit this neighborhood to be able to tell whether the target is really there or not. So when you look at this in 2 dimensions or in higher dimension, so for each possible target, you have this neighborhood that you should visit to be able to tell the target is there or is not there. So then this becomes like you have all these neighborhoods and you would like, I mean, a path that does not visit all the neighborhoods cannot distinguish between the targets, cannot distinguish between the prediction functions. So this becomes an Euclidean TSP with neighborhoods problem. So you need lower bounds from Euclidean TSP with neighborhoods. Okay. So basically what you want is a TSP that visits all possible disks of certain radius inside the bigger disk. And a lower bound of such TSP gives you a lower bound on any search strategy. Because as soon as you have still two of these people that you did not visit, the target could be in any of the two. Okay. So I think this is a nice connection to Euclidean TSP. So we use the standard lower bounds that have been used in previous research. Okay, so conclusions. So I was trying to talk about 2 points here inside in the intersection between computational geometry, or the search problem is not really computational geometry in the sense of it's not a running time, it's a search strategy, what we are discussing, but I think it's still fair to count that as computational geometry. So we have looked at 2 points here. So one of them is about the Delaunay triangulations, an Euclidean minimum spanning tree with predictions, and the predictions in this setting were objects that are similar to the one we are looking at, we are searching for. And then I introduce a new search problem. As I was mentioning, the upper bound and the lower bound here are way off, so that's definitely a space for improvement, a lot of it. Here, for the Delaunay triangulation of the Euclidean minimum spanning tree, some of our results are having some log stars or log-log-n factors that it's hard to believe that should be there. Okay, that's a standard kind of thing that one would not expect that should be there and that can be improved, but of course we do not know in general. And that's it. Thanks for your time.
Thanks.
So I didn't explain much about the ideas, but I mean, there are two kinds of ideas being used there. I mean, so one of them is this Oliver's De Villers. Another one that is being used is separators for planar graphs. So basically, once you're given a triangulation, you can use division, so that you divide the planar graph into pieces. And in general, some of these pieces, they should match very good with the Delaunay triangulation, and some of them you should fix. Okay. And depending on the scenarios, we use one or another approach. Thanks for the question.